Hi, Joanna.
Hi, ma'am.
How are you?
Fine, ma'am.
Okay. Okay, Joanna. Yesterday we have done till zeta potential, right?
Yes, ma'am.
Okay. Today we will be starting with purification of colloids.
Yeah, okay.
Is my screen visible to you?
Yes, ma'am.
Okay. So the topic we will be starting is purification of colloids. Okay. So purification of colloids means it is the process of removal of impurities from colloidal solution. Okay, wait a minute. Okay, yes, Joanna. Sharing the screen again. Okay, so the process of removal of impurities from colloidal solution, it is known as purification of colloids, right? For example, you have a colloidal solution with colloidal particles, and along with it in a beaker, you have true solution also. So you can say that if we are removing the true solution from this colloidal solution, okay, we will be removing this. So the removal of this true solution from this entire solution, it can be called as purification of colloids. Okay, now purification of colloids, it is done by three methods. It is done by three methods. The first method is dialysis. Okay, what are we doing in dialysis? In dialysis, the process of removal of You can note it side by side because today's part is all the theory part, okay?
Yeah,
Process of
okay.
removal of impurities from colloids via diffusion. Via diffusion through a membrane. Through a membrane is called as dialysis. Here it is, the process of removal of impurities from the colloidal solution via diffusion through a membrane. Now, which membrane can it be? We will be using the suitable membrane. So the membrane which is used in this, it is animal membrane. Which can be the bladder, okay? Or it can be the parchment paper, which can be used as a membrane, or here we can use cellophane sheet. Cellophane sheet. Okay, so these are the membranes which are used, and the apparatus which is used for this purpose. The apparatus used for this purpose is dialyzer. Dialyzer. Okay. Now, what is the process actually happening? We are taking a beaker which is full of water. At one end of the beaker, we have inlet for water. This is the inlet of water. Okay. In this, we have a can, you can say, or a beaker, you can say. Okay. This beaker, it has a dialyzing membrane on its wall. It has a dialyzing membrane, or we can say the membrane we were talking about for this. It can be animal membrane, parchment paper, or cellophane sheet. Cellophane sheet. Okay. Now here we have water. Okay, water is filled in this beaker, and in this beaker we have that solution which is the colloidal solution mixed with impurities. Okay, this is the colloidal solution which is mixed with impurities. So this solution, it must be having colloidal particles along with true solution. Okay, so we can write that it must be having the crystalloid, the colloidal particles, and the true solution. Okay, and yes. Okay, now what is happening here? Yes.
Crystalloid means what?
Crystalloid means the two solution particles. Okay, so we will be having the two solution particles. Along with it, we have the colloidal particles also. Okay, that will be somewhat bigger in size in comparison to true solution particles, right? True solution particles will be like this. Now we want to separate this true solution particles from this colloidal particles, right?
Yes, ma'am.
Yes. Then what are we doing? Here we have a small outlet. Okay. Now what we will do, this dialyzing membrane, it has small holes on its membrane part. Okay. These dialyzing membrane, it has small holes on this membrane part, and the size of these holes are equivalent to the size of two solution particles. Okay. The size will be less than 1 nanometer. Okay, so if the size of the holes on this dialyzing membrane, it is equal to true solution particles, then true solution can come out of these holes, right? Can true solutions come out of these holes if the size
Yes,
of
ma'am.
the, okay, so true solution particles will come out they will be coming out of this hole and they will be dissolving in this water that is outside in the big beaker. Okay. And after they are dissolving in water, so we have an outlet where we will be getting water plus the crystalloid particles or the true solution particles. Okay. And in the beaker, what will be left? We will be left with only colloidal particles. Understood? What is the phenomena happening for this dialysis?
Yes, ma'am.
Okay. So this was the first method for purification of colloid. Now we will be going to the second method. Okay. The second method is similar to this dialysis method. It is electrodialysis. Electrodialysis. Okay. Now the process of dialysis which we were seeing earlier, it was quite slow. Okay. So how can we speed up this dialysis process? We can speed up by applying an electric field. Okay. So if we are applying the electric field, then the dissolved substances are separating from from the solution of colloidal solution and the true solution particles. Okay, now how it is happening, I will be explaining you with the diagram only, and then we will be writing the theory for it. So the same setup we are taking here. We have one inlet in this big beaker, and here we will be having one outlet for this. Okay, the same a small beaker we will be having. Okay, the small beaker, it will be full of what? It will be full of crystalloid particles also, and it is full of true solution particles. Okay, now how we are taking the same this setup, because the core method is same. It is dialysis, but here we will be applying electricity so that the separation of colloidal particles and the true solution particles is increased. The rate is increased of their separation. Okay. Now here we are having water inside this. This is water. This will be the dialyzing membrane as it was in dialysis. Okay. And here this is the inlet for this water. Okay, these will be the colloidal particles, or we can say the sole particle, and these small here, it will be true solution particles, or we can say the crystalloids. Okay, now what is happening here? In electrodialysis, we are supplying the electricity with the help of two electrodes we are attaching here. Here we will be having the cathode, and here we will be having the anode. Okay, we can take this anode, actually make this inlet a bit lower. Okay, so here we are having the anode. This is anode and this is cathode. Okay, so this cathode will be, what will be the charge on cathode? This will be negatively charged and this anode will be positively charged. Now this anode and cathode, externally they are connected from an electric source. Okay, maybe they are connected from a battery. So when electricity is supplied, okay, these cathode, the electrode is already negatively charged. So which charge particle will it be attractive, right? And the
Last ma'am, your voice is breaking.
Okay, okay. Is it clear now?
Yes, ma'am.
Okay. I was saying that we have attached two electrodes, and these two electrodes, they are connected to an electric supply. Now cathode is negatively charged and anode is positively charged electrode. So cathode will be attracting the positively charged particle. That means it will be attracting the positive charged, and anode will be attracting the negatively charged particles, right? Now in this beaker, we have sole particles and crystalloids also. So if these are colloidal particles, they must be having some charge. They must be having positive and negative charge, right? So these negatively charged particles will get attracted towards cathode and positively charged towards anode.
Yeah.
So the true solution that we are talking about, the true solution or crystalloid, these particles will be having both positively charged electrode and both negatively charged electrode. Now we have placed 2 electrodes here, and here the solution has both positively charged and negatively charged. I am talking about only true solution. Why only true solution will get attracted? Because here we have a dialyzing membrane also, which is having holes equal to the true solution particle size, right? So only true solutions can come out of this. Now true solution particles have positive charge and negative charge. So these positively charged particles will get attracted towards cathode, and negatively charged particles will get attracted towards anode, right? So the
Yes,
speed
ma'am.
of these true solution particles coming out from this mixture will increase. And that is the purpose of electrodialysis. Okay, we are speeding the process of dialysis, which is quite slow if we are not using the electricity in this. Okay, if we are not supplying the electricity. Understood? What is the
Yes, ma'am.
core idea about electrodialysis?
Yes, ma'am.
Okay, now we can write the theory for this, and we will be drawing a clear diagram. Now here we have a beaker with an inlet, and here we have an outlet. This is inlet. This is the inlet for water, and this is will be the outlet for water and crystalloid. Here we have this beaker, and this beaker has colloidal particles which can be seen with the naked eye, but the true solution particles, they cannot be seen, so they will be in this beaker only. Okay, now these two solutions will have positive charge and negatively charged. Okay, so here we have cathode, which is negatively charged. Cathode, this is the dialyzing membrane. Okay, here we have anode, positively charged. Okay, here we have these soul particle, and along with it we will be having the crystalloid. And this whole beaker, it will be filled with water. Okay, understood? Now what do we need to write in this? We need to write that as the process of dialysis is slow, so it can be, so it is made faster. It is made faster by point you can write that the colloidal solution the colloidal solution is placed in a bag of suitable membrane with pure water outside. The ions present in the colloidal solution migrate to the attached a positively charged electrodes. Okay, and the process is known as electro dialysis. Clear, Joanna? Dialysis
Ma'am,
and electrodialysis.
yes, ma'am. And the third point, the ions present in the solution migrate to the attached what?
Attached a positively charged electrodes.
Okay.
The ions will migrate to the positively charged electrons, right? Because positive ions will migrate to the cathode and negatively charged ions will migrate towards the anode.
Okay, ma'am. Clear.
Okay, so these were two methods, and the last method which is used for purification of colloid is ultrafiltration. So what is an ultrafiltration? First, I will explain you the process, then we will write. Ultrafiltration is a type of method in which we are converting our normal filter paper you must have seen in your lab, right? So we are
Yes, ma'am.
converting that normal filter paper into a special filter paper. Then how are we making this special filter paper? This special filter paper, it is made by soaking the normal filter paper in colloidal solution. Okay, I will explain you about colloidal solution. And after it is dipped in colloidal solution, it is soaked in colloidal solution, it is dipped in formaldehyde. Okay, then it is dried. So after dipping in formaldehyde, it becomes hard and then it is dried. Okay, so what happens actually in ultrafiltration, we are converting our normal filter paper into special filter paper. The first point is this. Second point is special filter paper is made by soaking the filter paper in colloidal solution. Okay, colloidal solution, then hardening by the formaldehyde. Okay, and finally drying it. Okay, now what is colloidal solution? Colloidal solution. Colloidal solution is 4% solution of nitrocellulose with mixture of alcohol and ether. Okay, so this normal filter paper, it is dipped in colloidal solution. After that, it is dipped in formaldehyde and it gets hardened and then it is dried. So what happens that it can be used for purification of colloids. Okay, after it is dipped in all these and it is finally dried, right? So what happens to the filter paper? On the filter paper, it forms such pore size that is equal to the particle size of true solution. So if the filter paper, actually this is the filter paper, and it is it develops it molds in it. Okay, those molds is so if pass a particle and solution in it, solutions will pass through this filter. Colloidal particle remain on this paper. Will remain on this
Ma'am, your
particles and will extend the yield.
ma'am.
Okay, till which topic did you get? Wait, let me change my network. Wait. Joanna, it is fine now?
Yes, ma'am.
Okay. Till which topic you got?
Till the third point, it forms such pore size that is equal to the particle size of the solution. That's it.
Of the true solution. Of the true solution particles.
Okay.
Okay. So if the particle size, so this is the filter paper, and after the whole process that we have done in 2 points, okay, this filter paper, it develops holes in it, and the size of these holes is equal to the particle size of true solution. Okay, so if I am passing a mixture of colloidal particles and true solution particles, then if the hole size is equal to true solution particles, then true solution particles will pass through this filter paper, right? And what will happen to
Yes,
the colloidal particles? It will remain on the filter paper. Okay, then we can dry those colloidal particles and we can extract them. Okay, so by this method also, we can purify the colloidal solution or the colloidal particles. Okay, is equal to the particle size of the true solution. So it can pass through the filter paper. Through the filter paper. Is this method clear? All the methods are clear?
Yes, sir.
Okay, so these 3 methods, they were for the purification of colloids. Okay, have you noted it down?
Yes, ma'am.
Now we will be moving to the properties of colloids, and in the properties of colloid, we will be doing 4 of its properties. Okay. Properties of colloids. Okay. So for this first property is colligative property. What were colligative properties that you must have studied in your solution chapter? Remember?
Those who do not depend on the nature of the solute.
Yes. So on what do they depend? They depend on the number of solute particles. Right?
Yes.
The number of solute particles. So the same property is of colloids also. Okay. That colloids exhibit the property of colligative one. So they depend upon the number number of solute particles. Now, if you have the colloidal particles of same order as compared to true solution at same concentration, okay, I am taking the colloidal particle, of same order as compared to true solution at same concentration. Okay, if we are taking it to be a same concentration. For example, you have your colloidal particle, okay, and you have your true solution particle, and we want to fill these particles in a beaker, in two separate beakers, which have a concentration of 1 molar for both. Okay, so if I want to fill these colloidal particles and these two solution particles, for which the number of particle will be more, because we know that particle size of colloidal particle is more than true solution particle, right? Particle size of
Yeah. So
colloids is more than true solution particles. So can I say that number of particles of true solution will be required more than colloids to be filled in the same
yes, ma'am.
concentration? Okay, so number of particles for colloids, it will be less than true solution. So got it? What I was trying to say, that how does it depend upon the number of solute particles? If we want to fill
Yes.
these, if we want to take these both particles to same concentration, then the number of true solution particles will be always then the more than number of colloidal particles, because the size of colloidal particle, it is more than true solution. Got it?
Yes, ma'am.
Okay. This was the first property of colloids. Now we will be doing the second property. The second property is, if you have here, Tyndall effect. Tyndall effect. Now, what is this Tyndall effect? Tyndall effect is the scattering of light by colloidal solution. The scattering of light by colloidal solution is called Tyndall effect. Okay. Now, this Tyndall effect I will be explaining using one diagram. Let me take that diagram. This and one more. Okay, not this. This diagram from your NCRT. We will be seeing this afterwards. First, see this diagram. If you see in this diagram, then if the light beam is coming and it is passing from a beaker which is containing true solution, okay, then what is happening to this true solution? The light is passing and we are not able to see the true solution particles. Why? Because these solution particles, they are so small in size that they cannot be seen with a naked eye. Okay, but if you see in the second beaker, then you have colloidal solution, and the colloidal particles, they can be observed when light beam is falling through the beakers. Okay, so this effect is known as Tyndall effect. Now, we can see that light is passing through this colloidal solution and light is being scattered. So this scattering of light by the colloidal solution particles or by the colloidal solution, it is known as Tyndall effect. Now, if you have observed that if in your home, you must have your window and early in the morning, you must have seen that sunlight, the ray of sun is coming through the window into your room. Have you observed it? You must have seen in
Yes,
that
ma'am.
ray of light, you must have seen many particles, small particles are there.
Yeah, dust particles.
Yeah, dust particles are there. So how are those dust particles, how can you see the light coming? Because those dust particles, they are scattering that light. Okay, and due to the scattering of light, you can see that light. Okay, why the sky color is blue? It is because of the particles that are present in the atmosphere. When the light is falling on that dust, on those particles, they are scattering the light, okay, in such a way that we are able to observe that sky to be blue. Now, why it is blue? It depends upon the wavelength of light that is falling on those particles. Okay, so the wavelength of light that is falling on those particles and the light that those particles are scattering. So the color depends upon that wavelength that is falling on those dust particles. Okay, that is why the sky appears to be blue. Okay, so this was the diagram which was giving you an idea of a beam of light. If you observe in this diagram, here we have a light source and here we have a tyndall cone, and this light is passing through a tyndall cone and it is falling onto this colloidal solution. Okay, now these colloidal particles which are present in these colloidal particles, they are scattering the light in many directions. Okay, and here we are observing through microscope that these small colloidal particles, they are scattering the light, and the light which we see after this beaker is because of the scattering of those light by the dust particles, by the colloidal particles. Okay, so this phenomena, it is known as Tyndall effect. Clear?
Yes.
Okay, so we will be writing about this. Okay, Tyndall effect is observed when it is observed when the diameter of dispersed particle is not much smaller than the wavelength of light. Now, what are we writing in this point? Tell me when you have written.
Yes, I'm done.
Okay. Now I am saying that diameter of the dispersed particle is not much smaller than the wavelength of light, then only Tyndall effect will occur. Now what does this mean? That this light source which is coming from here, it must acquire a wavelength. Okay, it must be having a wavelength. Now when this light with a specific wavelength, it is falling on these colloidal particles. Okay, if the diameter of this dispersed particle, it is much smaller in comparison to the wavelength, so these colloidal particles won't be scattering that light. Okay, because they are very small in size as compared to the wavelength, so Tyndall effect won't occur. Okay, after all, what is Tyndall effect? It is the scattering of light by the colloidal particles. If the diameter of these colloidal particles will be very small, then Tyndall effect won't occur. Understood?
Yes, ma'am.
Now the second point is Tyndall effect is used to distinguish between true solution and colloidal particles. Now, can you tell me how will it distinguish?
If it scatters the light, then it is colloidal solution. If it does not, then it is true solution.
Yes, very good. Third point is suspension may or may not show Tyndall effect. Okay. Now, what is this Tyndall cone? This Tyndall cone, it is bright cone of light. Okay. Okay. So this was Tyndall effect. Okay.
Yes.
So this was the second property of colloid. Are you done with it?
Yes.
Okay. Now we will be moving to the third property of colloid, that is color. Okay. The color of colloidal solution. The color of colloidal solution depends on wavelength of light scattered. This is the point that I have told you. Okay. For example, in a beaker, we have colloidal particles. Okay. And for example, the color of solution we are able to see is blue. Okay. Now, why it is blue? It is because the wavelength of light that is coming from here, that is passing through the Kindle cone, the wavelength of light that is striking these colloidal particles, they are scattering the colloidal particles, and the color of this colloidal solution is because of this scattering, and the scattering depends upon the wavelength. So can we say that the color of colloidal solution, it depends upon the wavelength of light scattered?
Yes, ma'am.
Okay, the same phenomena is the same phenomena that is happening in the sky, because the wavelength of light is such that that sky appears to be blue. Okay, it if the wavelength is of more if the what can I say, if the color is of more wavelength, then that color will be visible. If the wavelength light is shorter, then that color will be visible. That is why it depends on, we are able to see red color, blue color, all the colors that we can see around. It is because of the particle, the light that is falling on those particles, and the color we are able to see is because it depends upon the wavelength of light that is striking. Okay, so the color of colloidal solution, it depends upon the wavelength of light scattered. The second point in it is the wavelength of light depends on size and nature of dispersed phase. That means the wavelength of light, it depends upon the colloidal solution, the size and nature of the colloidal solution. Clear?
Yes,
So
ma'am.
this was the third property. Now the fourth and last property for colloid is Brownian movement. Brownian movement. Okay. So what is Brownian movement? The continuous zigzag motion of colloidal particle by unbalanced bombardment of particles of dispersed phase and dispersed medium. Now what I am saying, I am saying that, for example, in a beaker, I am saying that you have colloidal particles also, and you have a mixture of two solution particles also. Okay. Or we can say that I have a mixture of colloidal solution particles, which is the dispersed phase and which is dispersed in some medium. Okay. Or I can say that I have gel as a dispersed phase, and any medium I can add, any liquid. Now the particles of these dispersed phase, and there will be also be the particles of dispersed medium. Now, if these two particles, they are in a small beaker in a fixed volume, then these particles will be colliding with each other. Okay. And
Yes,
they
ma'am.
will be bombarding with each other. So the continuous zigzag motion of these colloidal particles. Now, if this colloidal particle, it strikes, so it will be showing the movement like this. From here, it will be going like this. From here, it will be going. So it will be going, it will be showing a zigzag movement. So that zigzag movement of any particle, okay, that is present in the dispersed phase and dispersed medium solution, it is known as Brownian movement. Okay, that zigzag movement motion is known as Brownian movement. Okay, now I will be writing you the points and you will be able to understand on your own. Smaller the size and viscosity of solution. What is viscosity? Resistance to flow, right? Viscosity.
Now, what I remember is like when we put a ball in water, it will fall faster than when we put it in honey. This is viscosity. like
Yeah.
that as well.
So what is that? Yes. What is that? It is the resistance to flow. That means that if you are falling a ball in water, it is falling faster because the resistance of the solution is less. And if you are falling in honey, then the resistance is more. It is resisting that ball to fall with a with a greater speed. Okay. So viscosity is resistance to flow. So if we have a smaller size and if the viscosity of a solution is less, okay, faster is the movement of the particle, right?
Yes, ma'am.
Faster is the movement of particle. Okay. Now the third point is it produces stirring effect. Stirring effect. Now, what is the stirring effect? The stirring effect is the continuous movement of the particle, you can say. It is the stirring effect. The particle is running and running and it is showing the stirring effect. So it produces the stirring effect which does not permit the particles. So if it is continuously moving, it will not permit the particle to settle down, to settle, and thus is responsible for the stability of source. Okay, this was the fourth point, and the last point for this is the motion of particle. The motion of particle is independent of the nature of colloid. Okay, so these were the 4 points that you need to write in Brownian movement, and these were the properties of colloids. Which property we have done? We have done colligative property, Tyndall effect, color, and Brownian movement. Is it clear, Joanna?
Yes, ma'am.
Okay. Now we are done with these two main topics, and now we have the part which can be done in a single lecture. Okay. Our next lecture will be the last lecture for surface chemistry.
Okay.
Okay. Okay, Joanna. Written?
Yeah. Thank you, ma'am. Yes, ma'am.
Okay. Okay.
Thank you, ma'am.
Okay.